Well, hello everyone. Let's get started with today's lesson on ionic bonding. You can find that lesson 3 in your study guides. So let's get started with this topic. Turn to lesson 3. All right, now that we've had some time to talk about some basic principles of chemical bonding, such as why bonds form in the first place, and what is a Lewis symbol and how to draw a Lewis symbol, we're now free to begin discussing our very first bond type, ionic bonding. So let's start out with what is an ionic bond in the first place. So by definition, we would say an ionic bond is an electrostatic attraction or force, right? Attraction or force between oppositely charged ions. So just as the name applies, ionic bonding, we're going to create a bond or a force between two differently charged ions. All right, so let's use our tennis ball idea here. So let's say we have an atom, and this is going to be a metal atom. And this metal is going to lose electrons. It has low ionization energy, so it loses its valence electrons. And it's going to do that in order to have a full valence shell, all right? But the problem is that it's going to be positively charged. So it's a cation, all right? And we know that metals form cations based on losing their valence electrons. So here's our cation over here. At the same time, we have a non-metal atom. And this non-metal atom, instead of losing electrons, it's going to go ahead and gain some electrons to form a full valence shell. But its trade-off is it becomes a negatively charged ion, or an anion, essentially. So these two atoms are now charged, positive and negative. So what's going to happen is, because of their charge, they might have full shells, right? Full valence shells, which is what they desire the most. The problem is that they're positive and negative. And positive and negative atoms are not really energetically favorable, all right? So we kind of have this problem where, yes, we needed to lose and gain electrons in order to have full valence shells to satisfy the octet rule. But the problem is we create ions or charged atoms in the process. Not a good situation. So to overcome that, these two ions, because they are opposite in charges, are going to attract one another. By attracting one another, they form that force or ionic bond, electrostatic attraction, between these two ions. And now they become a package deal. They come together, all right? Now, by doing that, the charges, the positive and negative charges, balance out, and they offset one another. And this will satisfy the demands of the high potential energy state to a lower potential energy state. But they have to stay together. They have to stay bonded, the positive and negative, to balance out that charge. Okay? So let's actually diagram a situation like this. Let's take an easy one. Let's take sodium. Sodium is a metal. It has one valence electron. And so if sodium ionizes that one electron, gets rid of it, removes it, then it will become a positively charged atom. Okay, so I'm going to draw that right now. It's lost an electron, it becomes positively charged. Okay. Now, by becoming positively charged and losing that one electron, sodium now has a full valence shell. And so it does have a complete octet, which is what it wants to have to become like a noble gas. The problem is it's positively charged, okay? And that creates itself its own energetic problem. And that is, now that it's positively charged, it's going to have a higher potential energy. So what we're going to do is try to balance out that charge with a negatively charged ion. So let's say we have chlorine. Now, chlorine needs one more electron to have a full valence shell. And since chlorine is a nonmetal, it doesn't readily get rid of electrons. Instead of it gains electrons, like any nonmetal. So chlorine is going to gain an electron, becoming negatively charged. Again, that's a great thing on the fact that it has a full valence shell now. It's going to have a full octet. But the bad thing is it's negatively charged. So sodium and chlorine go, hey, you're negative, or you're positive, you're negative. Let's hook up, all right, and balance out our charge, and therefore we'll be happy. The only thing is we have to stay together. We have to stick together now, all right? And so they're going to do that, and they're going to create this bond between each other as a trade-off of balancing out their charges. And that bond is known as the ionic bond, okay? Let's look at another one real quick too. Let's say we have magnesium. Magnesium's a metal. It has 2 valence electrons, so if it gets rid of those 2 valence electrons, it will have a full valence shell now. But it does also create the positive charge problem. And in fact, it is now more positive than sodium, which makes it even worse, because the more positive the ion is, the more energetically unfavorable it becomes, okay? So we need to balance out these 2 positive charges. Essentially, magnesium somehow needs to bind, form a bond, an ionic bond, with a nonmetal that will allow it to balance out those charges. So let's say there's a chlorine. Well, we just talked about the fact that chlorine only needs to gain 1 electron. It's not going to gain 2 electrons. So chlorine would only gain 1 electron, become negatively charged. Well, this might balance out one of the positive, but not both of them. So we have a problem. Yes, we can form a ionic bond between magnesium and this one chlorine, but we still have an excess of 1 positive charge. That's just not good. So what we're going to do is we're going to strategize a little bit, and there's probably going to be more chlorine out there, right? Yes, there will be. So what will happen is the magnesium is going to bind to another chlorine anion. Now we have 2 negative charges and 2 positive charges, and those 2 will balance out. So now, though, there's going to be a package of 3, right? So the magnesium and the chlorine are going to come together as a package deal. And we now have 2 ionic bonds that have been formed between magnesium and one of the chlorines, and magnesium and the other chlorine, okay? Now, to simplify all this bonding, ionic bonding down, we typically write a formula, okay? So for the sodium chlorine, we would write a formula of NaCl. We typically drop the charges, indicating that we have a good balance of positive and negative. Now, it doesn't mean that the positive and negative charges have gone away. They're still there, all right? That's what creates the attraction in the first place. But we can eliminate them from our formula to let the reader know, or who's ever looking at that we have a balance of charge, positive and negative, okay? And so in this case, we form an ionic bond of a 1 to 1 ratio. Now, we don't necessarily have to put those ones there. We normally don't, right? But we do have a 1 to 1 ratio, 1 sodium to 1 chlorine, in order to reduce or cancel out those charges. And so the ratios are important here because they are used to indicate how many of these atoms we need in order to balance out or offset the positive and negative charges. So for instance, for magnesium, our formula would be MgCl2. Okay, again, we've dropped the charges up here because now it indicates to us that we have balanced charges. We have the same number of positive and negative, all right? But what we need to do is have the ratio between those atoms those ions. So it gives us a better understanding of how many atoms we needed to balance out the charges in the first place. So in this case, we needed 2 chlorine atoms to balance out 1 magnesium atom. So we have a ratio of 2 chlorines to 1 magnesium, or a 2-to-1 ratio there, okay? Hopefully that makes sense. So the ratio is important in an ionic bonding situation, because the ratio indicates how many atoms we needed to offset those charges, all right? Now, the other thing we can assume then is that once this occurs, not only do we have the ionic bond, but we can assume that the metal, magnesium in this case, has a full valence shell, and the chlorines, each of them also have full valence shells. So at this point, all atoms that are involved in this situation are going to be at low energy states, low potential energy states, and everyone's happy and hunky-dory. They just have to stay together. They have to stick together. They cannot separate, or that defeats the whole purpose of creating low energetic states for these particular atoms, okay? So that's the beginning of ionic bonding in a nutshell there. All right, so let's go through the whole process of how an ionic bond is created in the first place, okay? We're gonna model this, all right? We're gonna model this using our sodium chloride, or our sodium atom and our chlorine atom, okay? So what we have created is a simple Bohr model or shell model to help us to see what's going on here in forming this ionic bond. So if we look at the shell model for sodium, you will notice that sodium in its valence shell has 1 electron, right? This one sole electron. Well, if sodium can get rid of that 1 electron, all right, ionize it, it will then have a new valence shell. And look at the next shell in, right? How many electrons are in that next shell? Well, there's 8 of them. Look at 1, 2, 3, 4, 5, 6, 7, 8. So if sodium can ionize this 1 electron, it will now have 8 electrons in its valence shell, which will make it a full electron shell, or a complete octet. So the metals, just like sodium here, their strategy to create full valence shells are actually to lose their current valence electrons, all right? That's the game they're playing here. Once they lose their valence electrons, their new valence shell now is full, all right? Now, at the same time, the nonmetals, let's use chlorine, the nonmetals are going to play the opposite game. Instead of losing electrons, because they have very high ionization energy, so they can't really get rid of their electrons very easily, it's easier for them to actually pick up electrons. So if sodium loses 1 electron, there's a free electron now available for the nonmetal, chlorine, now to pick it up. And once that chlorine adds an electron to its valence shell, now it has a full octet and a full shell. Look at this, 1, 2, 3, 4, 5, 6, 7, 8. 8 electrons around that shell, okay? And we're pretty good, okay? Now, let's look at the electron configuration, and then we'll finish this up. So if you look at the electron configuration of sodium, the valence shell is the 3s1, okay? That 1 electron, which is what's going to be lost, this 1 electron, and it's going to be transferred. So what we're going to call it transferring, or transferring its valence electrons to the nonmetal. Well, the nonmetal for chlorine, this is its valence shell, the 3rd shell, right? And it has 2 electrons in the 2s or 3s, and 5 electrons in the 3p. It only needs 1 more electron, and it becomes like a noble gas, all right? So chlorine is easily going to accept one electron to fill its valence shell. And so if you look at the new valence electrons for these new electron configurations, for sodium, it's now the second shell because it's lost the electron in the third. And notice it's going to have a full shell now. 6 plus 2, 8 electrons. For chlorine, it didn't lose a valence shell. It just gained one more electron, and now it has 8 electrons in its valence shell, which is the third shell. Okay? And so this is the game that these ions are going to be, or these atoms are going to be playing. The metals are going to lose electrons in their valence shell, and the nonmetals are going to take them to get full shells. So that way, each element or each atom, metal, nonmetal, is going to have a complete octet or full shell, which is going to lower its potential energy. The only bad thing, the only negative thing to this strategy is that you create the positive and negative ions, right? As a result, the sodium becomes +1 and the chlorine becomes -1. So by themselves, they create an unfavorable situation. To rectify that, the two ions are going to come to an agreement. The metal and the nonmetal, cation, anion, are going to say, hey, if we bond together, if we form an ionic bond, then we can offset those charges, balance it out, and we're good to go. The only thing is we have to be stuck together. We have to stay together. And so that's what will happen is we're going to form this ionic bond between the sodium and chlorine, right? So again, the steps are number 1, to create an ionic bond. To create an ionic bond, the metal has to transfer its valence electrons to the nonmetal. That's the first thing that has to occur. This results in a positively charged cation, okay, and a negatively charged anion, okay? But the shells are filled. Now, the last thing that has to occur is the opposite charged atoms must form an electrostatic attraction that holds those two ions together to form the ionic bond, okay? So that's how we make ionic bonds. But by definition, an ionic bond is not a transfer of electrons. That's just a process. The definition of an ionic bond is an electrostatic attraction between oppositely charged ions. So make sure that you're very clear on that. The process is transfer, but the ionic bond is the actual attraction of the two ions, okay? I want to make sure that we're clear on that. All right, so here's a little bit more information that you should write down in your notes to have this solidified. So why do metals lose their valence electrons? In other words, why are they able to take this strategy and have that ability? Well, we know that, first of all, that metals have very low ionization energies, right? With the low ionization energies, it gives them the advantage of being able to transfer valence electrons to the nonmetal. Nonmetals, they don't have that ability very easily. They can't lose their electrons because they have higher ionization energies. So instead, the nonmetals, they're going to gain their valence or gain new valence electrons to fill their shells. All right. So ultimately, if they ask you the question, why do metals take on the strategy of losing their valence electrons? It's because it's easy for them. They have low ionization energies. So they can say goodbye, get gone, good rhythms to those valence electrons, because now I have a new valence shell that's full. And it was easy to do. And so that's the strategy that all metals are going to take, okay? So keep that in mind as we're going through bonding here. Okay, here's a few other examples. So we have calcium and we have oxygen. Now, calcium has 2 electrons in its valence shell that needs to go bye-bye. They need to ionize, okay? If calcium can lose both of those valence electrons that are in the 4s subshell to another atom, then it's going to have a new shell, new valence shell. If you count 1, 2, 3, 4, 5, 6, 7, 8, right? So that's the strategy it's going to do. Well, oxygen over here, hey, oxygen is like, hey, calcium, let's do this. I need 2 more electrons, right? Oxygen has only 1, 2, 3, 4, 5, 6 in its valence shell. I need 2 more, right? You give me those 2 electrons that you don't want anyway, and I'll take them. And calcium says, you bet. That sounds like a great idea. So oxygen grabs those 2 valence electrons. Now calcium will have a full valence shell. The 3s is now full, and the 3p is full. So the whole third shell is full for calcium now. Has 8 electrons in there. And oxygen will have 8 electrons in its valence shell now by picking up those 2 electrons, right? So everything looks good. Sorry, the lights went out. Everything's looking good for calcium oxygen. The only drawback, remember, is we're creating the positive and negative charge. But in this situation, we have 2 and 2, 2 negatives and 2 positives. So this makes for a great match, because oxygen says, hey, you know, I'm negatively 2 charged, you're positively 2 charged, so all we need to do is stick together. So we'll just create an ionic bond, we'll stick together as a package deal now. Well, wherever you go, I'll go, and so forth, okay? And as a result, we'll both have full valence shells, we'll both have low potential energy states, and we can exist in a happy situation. And indeed, that's what occurs, okay? Calcium transfers its 2 valence electrons, oxygen picks them up, the 2 ions come together, form an ionic bond, and balance out the charges, negative and positive charges, okay? All right, let's do one more example. We sort of did this already, but we're not using chlorine, we're using fluorine here. So magnesium, again, needs to lose 2 valence electrons to have a full shell. And so fluorine is nearby, and fluorine says, well, you know what? I'll be glad to take one of those electrons, right? I need one more, because here's fluorine's electron configuration. Its valence shell is the second shell. It has essentially 7 electrons, right? 5 plus 2, 7. All I need one more electron in my 2p, and I'll have a complete shell. But magnesium's like, ugh, shoot, I need to get rid of 2 of them though. And fluorine's, well, I'm sorry, I can only take 1. But he says, I have a buddy, I have a friend, right? And my friend needs an electron, right? So the fluorine goes and grabs another fluorine, his friend, and the fluorine goes, hey, I'll be glad to take your other electron, and it does. So magnesium goes ahead and transfers both electrons to each of the fluorines, right? And now, as a result, every element has a full valence shell. The 2 fluorines are happy, and the magnesium is happy. The only difference, or the only bad thing, again, is the negative charges in the positive charges. But no big deal, because as long as the fluorines and the fluorines and the magnesium bond together, forming an ionic bond, those positive and negative charges now offset. They cancel out, and everyone's good. They just need to stick together now. The 2 fluorines and the magnesium need to go as a package deal, all right? And they need to stay together, all right? Now, we do represent that, right? We Mg, right? Magnesium, fluorine, and we show the ratio of 2 to 1. 2 fluorines to 1 magnesium, right? We don't show the charges because those charges have been offset, they've been balanced out, and we're good to go, all right? But the ratio is important, all right? And that ratio is fixed. It must come as a package or a group, okay? At all time. All right, so there we go. All right, one more thing I want to just discuss. Oh, got a cartoon. Here's our cartoon for the day. I lost an electron, right? One atom says, I lost an electron. The other atom says, are you positive? Okay, bad Kim joke. Here's another one. If you know anything about James Bond, the name's Bond, ionic bond, taken, not shared. Got it? Taken, not shared. Yeah, you'll understand more about that when we get into covalent bonding, about sharing electrons. Okay. Anyway, 2 jokes for the day. All right, now let's wrap this up. So I want to conclude this lesson by talking a little bit about what we call ionic compounds. Okay. Now we're going to spend a lot more time later on in the year discussing what an ionic compound is in greater detail, especially the properties that are associated with ionic compounds, okay? But essentially, as the name implies, ionic compound, it's made up of ions. So what's going to happen is those situations that we just looked at represent all of those ions that are positive and negatively charged are going to really come together as a large crystalline group. And they're going to start forming these large compounds known as ionic compounds. So what we can say is an ionic compound, by definition, are solid crystals for the most part. They're solid crystals that form when a metal and a non-metal ions are held together by ionic bonds, okay? So positively charged atom, negatively charged atom come together, but we have tons of these, right? Tons of these tennis balls that are positive and negative. And they're all going to come together and they're going to create this large crystalline structure, okay? And let me show you some examples. Right here is a real example of an ionic compound. This is made up of sodium and chlorine ions, okay? Now, sodium and chlorine ions, those ions are really small. So to make this crystal structure, this has got to be hundreds and hundreds of thousands of these positive and negative ions that are forming ionic bonds to create these crystal structures or ionic compounds, okay? So that's what you got to think about, is that usually we're not talking about one ion and one ion coming together. We're talking about hundreds of thousands of these ions forming ionic bonds, hundreds of thousands of ionic bonds to form one coherent group called an ionic compound, okay? So here we kind of got the idea of, here's the sodium chloride crystals made out of sodium ions and chlorine ions. They attract by themselves, forming an ionic bond. But if we got tons of these sodiums and tons of chlorines, they're going to all form these ionic bonds between them, creating this nice crystalline structure, solid crystal, that we call an ionic compound, okay? Now, the ratio between the metal and non-metal ions in the crystal must stay the same ratio. So if we have our formula of sodium chloride, and we have a 1-to-1 ratio, we must always have 1 sodium to 1 chlorine. So within this crystalline structure here, we have to maintain that 1-to-1 ratio. So we have 1 sodium to 1 chlorine, 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 okay? That ratio is maintained throughout the entire structure, that entire compound, in order to keep the charges balanced or offset, all right? So the ratio is important in letting us understand that we keep that ratio to balance out the charges. But that does not tell us that we really have only 1 chlorine and 1 sodium in the compound. We can have hundreds and hundreds of thousands of these ions, but the ratio between those ions must stay the same. It cannot be altered. Because if we alter the ratio, we will not be able to balance out the charges anymore, and the compound will be unstable, and that is not good. Okay. Here's one last example. Okay. Here's an ionic compound. Okay. This is made up of sodium and fluorine. Okay. And makes the fluorite. It's really cool. Crystal. You can see these really crystals here. Okay. Made up of tons of fluorine ions. All right. So those are a couple of examples. Again, we will spend more time talking about ionic compounds later on in the year, but I just wanted to get you started thinking that these ions do come together. They do form an ionic bond, and as a result, they form hundreds of thousands of ionic bonds to create these ionic compounds, crystal structures, okay? Well, there we go. There's the basics of ionic bonding for this lesson. So yeah, that's it. So we'll see you guys later. Till next time.